Okay, the next part of this is about concavity. Concavity is talking about which way it's curving. Now, they define it in terms of what our derivative is doing. But really, maybe a better way to think about it is just which way it's curving. If I am going down, but I'm kind of curving, I'm tending to go up, then we would say that this is concave up. Whether that's just like this or whether it's like this, all those are concave up because what's happening is y prime is increasing. Okay, so if I look at this one, maybe my tangent line is going like this here, down here, and then it's getting steeper as we go. Okay, so we would say that y prime is increasing. Even with this one, I have a negative value, so even though it's getting less steep as we go, it would still be increasing because I'm going from a negative to kind of a less negative value. So as we move from left to right on this one, it's always increasing because I'm moving from negative to positive and then getting steeper. And so we say that these are all concave up. With concave down, y prime is decreasing. So the opposite thing is going to happen as we curve. It's always curving down like that. Or it might just be part of that, like either one of those. So we see that again as we move from left to right, the slope of the tangent line is decreasing. And that's how they define it. So if we want to test our concavity, since we're looking at where it's increasing or decreasing, if it's increasing, then its second derivative, y double prime, is going to be positive. So concave up, it's increasing. Concave down, the second derivative is going to be negative. So basically, to check for concavity, we do it the same way that we checked for maximums and minimums, except now we're looking at the second derivative instead of the first derivative. Okay, so looking for concavity on these intervals. So first of all, I've got y equals x squared, but I want to look at the second derivative of this, which is 2. Notice that no matter what, 2 is always positive, and so my second derivative is always positive. That means this is always concave up. If we look at the graph, it's a parabola, and we can see, yeah, that's always curving upward, whichever side it's on. On the next one, 3 plus sine of x. Okay, so y prime will give me cosine of x. The second derivative, negative sine of x. And so looking on this interval, so we'll start with endpoints at 0 and 2 pi. We want to consider where other zeros are on this interval. With the sine, the zeros are going to happen at 0. They're going to happen at pi and at 2 pi. So there's 3 places where we're getting a derivative of 0. Okay, these are endpoints, so I don't have to worry about them too much. Let's check what's happening between them. So first of all, there's negative sine of x, so these are all going to be negative. These are all going to be positive. And so we would say we are concave up on this interval. We are concave down on this first interval from 0 to pi. Now we have a point here where this changes. Okay, so here at pi, it's actually 0. And what we call this point then, on the next page, is called a point of inflection. That's where we're going to change from positive to negative on these. And so for first derivatives, we look for critical points. For second derivatives, we call them points of inflection. When we're looking for points of inflection, this maybe more corresponds to like maximums and minimums. Is what we're looking at. Now, for this definition, notice it says a point in the graph of the function has a tangent line and where the concavity changes. So this having a tangent line is important because if I have a function that does something like this, it's concave up and then it's concave down. But at this point, I do not have a point of inflection because even though this is concave up and then concave down, there is a change there. But if the derivative doesn't exist there, then it's not a point of inflection. What we need for a point of inflection basically is a smooth curve. Now, it could also even be a vertical tangent line. That would be okay if it's a vertical tangent line. Okay, so maybe your derivative doesn't exist there, but if that tangent line is a vertical line, then that's okay. But we just can't have a corner there. Okay, so if I want to find the inflection points of a function, we need to find the second derivative of it. The first derivative here, using the chain rule, is going to give us e to the negative x squared times negative 2x. For our second derivative, we're going to have to use the product rule. So I'll start with the derivative of this part here again, times the second part, plus the first one, times the derivative of the second. These will give me 4x squared. That'll give me minus 2. I'm going to factor out the e to the negative x squared. And then we want to look at where that, since it's our second derivative, we want to know where that's equal to 0 in order to find those points of inflection. So again, the e to the x can never be 0. It's also always going to be continuous. Not going to have any weird jerks there. Does not exist points there. It's just going to be 4x squared minus 2 equals 0. Which is plus or minus the square root of 1/2. Now we're going to check that with the table to see what these are actually doing on either side of that. Because we're looking, again, for a change in signs here. It's not enough that these are zeros. We need to have a change in sign as well. If I go back and plug into my second derivative function then, so we're looking, these are my x values, these are my y double prime values. I'm going to be getting a positive in this interval, a negative in this interval, and a positive in this interval. Because we're just looking at here, the 0 would give me negative 2, either side's growing. Okay, so my points of inflection then, usually they're looking just for the x values, even though they ask for the point, which would technically be the x and y. Usually we just want to know what x's those are at. So we're going to say at x equals positive or negative square root of 1/2. And we see that here on this graph here. Notice here it's curving up and then it starts curving down. It's hard to see exactly where that's happening on these, but now we found exactly where that's happening. Okay, now there's a worksheet. It's in the library on Edmodo. And if you have any questions, post them on Edmodo. I'll try to get back to you as soon as I can.